Hello, my dear students and the rest of the learners. Welcome to part 26 of a that 7-part series of tutorials in computer structured programming in C and Pascal. This is section 5 of 13 in the topic data structures. My name is MemJM, or you can simply call me EMELISWAP. In this tutorial, I'm going to look at sorting techniques, whereby I'll focus on bubble sort, selection sort, insertion sort, quick sort, and merge sort. Let's commence by looking at sort techniques. Sorting is the process of arranging data in a certain order, such as ascending or descending. Some of the most commonly used sorting techniques include bubble sort, also called sinking sort. We have selection sort, insertion sort, quick sort, and merge sort. Let's look at bubble sort. It is called bubble sort because the smaller values gradually bubble their way upward to the top of the array, like air bubbles rising in water, or the larger values sink to the bottom of the array. The idea behind this algorithm is to scan through the list looking for two adjacent items that are out of order. When you find two such items, you swap them and continue down the list. You repeat this process again from the top to bottom until all the items are in order. So, the values in the array are compared to each other, a pair at a time, and swapped if they are not in back order. That is from the smallest to the highest. The lowest value finally floats to the top of the array, like a bubble in a glass of water. If the comparisons are made from top to bottom, each iteration of the outer loop results in the largest remaining element sinking to bottom, and this last value is in a sorted position. The sorting for inner loop is completed in n-1 iterations of the outer loop. N stands for the total number of elements being sorted. If, for example, you have 10 elements, then it means that by the time you're performing the 9th iteration, that is 10 minus 1, the elements in the array will have been sorted out because the last element would already be in its sorted position. Though there are a certain number of elements in the list, the last element is automatically in place when n-1 elements are brought to their correct positions. This means, just as I have said, that if, for example, your array contains 10 elements, then by the time you're performing the 9th element, or once you perform, or once you check the 9th element, already the 10th element or the last element will already be in its sorted position. Bubble sort is easy to program, but it runs slowly because every exchange moves an element only one position closer to its final destination. This becomes apparent when sorting larger arrays. For example, if an array has the following elements, 60, 20, 10, and 40, then it's sorted using bubble sort technique in ascending order as follows. Note that in each step, elements written in bold are being compared. So in the first pass, we are going to compare the first two elements, that is 60 and 20. Then, if 60 is bigger than 20, as you can see, we swap the two so that 20 is brought forward and 60 takes the position where 20 was. And therefore, we have 20, 60, 10, and 40. So the first two elements are compared and swapped if they are not in order. That is, if the number which is in front is bigger than the second number. Next, we compare the second and the third elements. In this case, we compare 60 and the 10. In this case, we can see that 60 is bigger than 10. So we swap them, and therefore we have 20, 10, 60, and 40. So we swap since 60 is greater than 10. Next, we compare the third and the fourth element. So in this case, we compare 60 and 40. We can see that 60 is bigger than 40, and therefore we swap the elements since 60 is greater than 40. And therefore we have 20, 10, 40, 60. Now that we have been able to compare the elements up to the last element, then that is called first pass. So we proceed, we repeat the process again. And this is called second pass. So we compare again the first two elements, 20 and 10. In this case, we can see that 20 is greater than 10, and therefore we swap since 20 is greater than 10. And therefore we have 10, 20, 40, 60. Then we compare the second and the third elements, that is 20 and 40. Already we can see that 20 and 40 are already in order. And therefore, we have 10, 20, 40, and 60. So we don't swap since these elements are already in sorted order. Then we compare the third and the fourth elements. In this case, we compare 40 and 60. So because 40 is smaller than 60, we don't do any swap since these elements are already in sorted order. And therefore, we have our elements as 10, 20, 40, and 60. With that, we move again through the 30 pass. We begin again from the beginning. So we compare 10 and 20. Already we can see that those are in order. So we have 10, 20, 40, and 60. We then compare the second and the third elements, that is 20 and 40, and we can see they are already in order. So we have our array as 10, 20, 40, 60. Then we compare the third and the fourth elements, that is 40 and 60, and we can see that 40 and 60 are already in their possessions, and therefore we treat them as they are, and therefore we end up with our sorted array being 10, 20, 40, and 60. So the array is already sorted by the end of second pass, but as you have seen, my dear students and the rest of the learners, we continue with the algorithm. We continue with our comparisons until we compare the last two elements. So the array is already sorted by the end of the second pass, but our algorithm does not know if it is completed. The algorithm needs one whole pass without any swap to know if it is sorted. So the following is a sample program implementing bubble sort in C language. So just what I have explained, we do it by coding. So we have our comment, program implementing bubble sort through use of functions. So we have our preprocessor directive that contains the standard input-output functions, that is stdio.h. And then we define a constant called size, and we assign it to 8, 10. Then we have a function prototype called input array that receives or that has a parameter. And this parameter is an array parameter of type integer. Then we have another prototype called bubble. It is a void function called bubble that receives a parameter which is an array of type integer. The third function, which is also a void function, is called display array. It receives one parameter, which is an array of type integer. Then we have our main function. We declare an array for the scores of size 10 as defined by define size 10. So wherever we have the one size, we are referring to 10. So in this course 10, we have a second declaration of an array, or in other words, this statement here, my dear students and the rest of the learners, is not a declaration, but it is a call statement to the function called input array. So it is a call statement that is also passing to that function an array called scores. The next is a call statement that invokes the function called bubble, and it is also passing to that function an argument called scores, which is an array. Then we have our third, a call statement, which invokes the void function called display array, and we are passing into it one parameter or one argument, which we also called formal parameter, or not formal, but actual parameter, or what we just call argument, which is an array. Then we have return 0, which returns control back to the operating system, and that becomes the end of our main function. So because our function prototypes, or because we have prototyped our functions, we then define them at the end of our main function. So the first definition is for the input array void function that receives one parameter, which is an array. So it will receive one parameter of type integer, which is an array. Then we have local variable called int I. This function will display the statement, enter the input, or enter the scores, is sorted. Then this for loop that we discussed before in my previous presentations is meant to read the 10 elements. So we initialize I to 0. So in this case, I is our counter. So we initialize I to 0. Then we check if the value of I is less than 10. So is the value of I less than 10? Yes, because currently I contains 0. So is 0 less than 10? Yes. So we perform the following statement. So we execute the first statement, which is the first score, which is going to be stored in memory location called scores 0. That is in the first subscript or memory location or the array at the position which is identified or which is represented by subscript 0. So at scores 0. So the first value will be stored in the memory location which is scores 0. Then we increment counter. We increment the value of counter by 1. That is I plus plus. So 0 plus 1 becomes 1. Then we check the counter. Is 1 less than 10? Yes. So we need the next value, which is going to be stored in the memory location that is in the array at the section or at the portion represented by scores 1. Then we increment the counter again. From 1, we add 1, it becomes 2. We check the condition. Is 2 less than 10? Yes. So within the next value, which is going to be stored in the array at the subscript level indicated by scores 2. Then we increment the counter again with 1. So that process will continue, my dear students and the rest of the learners, until the value of I is not less than 10. So once I is 10, that means it will now be is 10 less than 10? No. So we are going to exit from reading of the scores, and then we display a new line. We print out a new line. Then that will be the end of our function. So that function is for reading the elements. The next function is for sorting the array in ascending order using bubble sort. Our function called bubble receives the array called scores, and already our array contains values. So we have 2 or 3 local variables, pass, j, and temp. So we use for loop to control the number of passes. So in the first pass, we initialize pass with 1. Then we check if the value of 1 is less than 10. So is 1 less than 10? Yes. So if it is less than 10, we move on again to the loop that controls the number of comparisons per pass. So we compare, in the first pass, we compare all the elements, one to the other, just as we have seen, and therefore we initialize j to 0. Then we check if the value of j is less than 10 minus the value of pass, so minus 1, the first pass. So is 0 less than 9 or less than 10 minus 1? Yes. So we check if the value in the memory location, which is scores 0, or scores, in this case, scores 0, is greater than scores 0 plus 1. That is the scores 1. So is the value in the memory location represented by the subscript scores 0 greater than scores 1? If yes, then we pick the content of a memory location called scores 0. We assign it in a temporary memory location. Then we pick the value in the second position or in the next position, which is scores 0 plus 1. That is scores 1. We pick the value there. We store it, or we assign it into the memory location called scores 0. And then we pick the value or the content in the temporary memory location. We store it in the second position, which is scores 0 plus 1. That is scores 1. And then we loop again. We move again. We check, or we move again to the for loop. We increment 0 with 1. So our next pass, we initialize j, or in other words, we increment 0 with 1, so it becomes 1. So is 1 less than 9 minus 1? So is 1 less than 9? In this case, it will be 8. So we continue that way. We compare, we swap. Remember, this portion here is for swapping. We pick a value that we want to interchange with the next. We store it in memory location called temporary memory location. Then we pick the value which is at the position that we want to replace. We store it in the position where we have removed the other value that we have kept in temp. And then we remove what is in temp. We store it at the memory location where we want to take it. And that continues until we are through with the first pass. So once we are through with the first pass, we increment the value of pass with 1. So we move on to the second pass, and then we continue again. We compare, we swap where necessary, we compare, we swap. And this continues the pass, the comparison and the passes. And the swapping continues until all the elements have been sorted. And that becomes the end of bubble sort. In other words, the end of sorting and the end of the function called bubble. And then we display the values from the sorted array using the function called display array, which also contains one parameter of type array. And therefore, we have local variable called I, which is counter. We display the message, the bubble sorted is called R. Then we use for loop to read the values and output them. So we initialize the value of I 0. So we check, is 0 less than 10? Yes. If it is yes, we pick the content of memory location called scores 0. What is in the array at or represented as subscript 0? That is scores 0. We display it out. We print it on the screen, spaced 4 characters. And then we repeat again. We increment the value of I with 1. So it becomes 0 plus 1, that is 1. So is 1 less than 10? Yes. So we pick the value in the memory location called scores 1. From scores 1, we pick that value, we display it on the screen, formatted 4 characters. So the 4D is for spacing purposes. Then we increment the value of counter, and that continues until the value of I is not less than 10. So once we have 10, is 10 less than 10? No. So we stop reading and printing out the values, and then we display or print out a blank line, and we end our function, or we stop outputting after all the 10 elements have been displayed. So this function is what I've explained. This is for displaying the sorted array. And with that, the next is a sample program implementing bubble sort in Pascal language. So here, my dear students and the rest of the learners, this program is similar, the one that I've already explained and illustrated using C. The only difference now is that we change the syntax. Otherwise, the logic and everything remains the same. So my program is called sorting. We declare this item that contains functions for manipulating the screen, like clearing. Then we are declaring, or we are declaring a memory location called size, which is a constant, and we assign it to 8. Value 10, we initialize it 10. And then we have 4 variables, temp, j, I, and pass of an integer. Then we declare an array called scores of size 0 to 10 of type integer. Then we begin, we clear the screen. This function is for clearing the screen. And then we enter the elements into the array. We request the user to enter the scores to be sorted, and then we use for loop to read the values using the same logic that I've explained in C. So within the first value, we store it in the memory location called scores 1. We increment the counter with 1 because the for loop is for I equals to 1, 2, 10. So we initialize I to 1. Then we perform the first reading, store the value. Then 2. 2 means we increment with 1. So 1 plus 1 is 2. So within the next value at the scores, we store it in the memory location called scores 2. Then we increment the counter again, 3. Within the value, and we store it in the memory location called scores 3. And that continues until when the value of counter of I will be equal to 10. So once we have for 10, I equals 10 to 10. Then we do our last read and we store, we write out a blank line using a write line. The next is a function for, or is the loop for sorting. This is the loop for sorting the array. So we initialize pass to 1. So for pass equals to 1, or for pass is equals to 1 to size. In other words, for the value of pass is 1, 2, 10, to begin. So we start our comparison using the inner for loop. Just as I've explained, we read or we compare our first two values. And then if they are not in order, we pick the content of the first portion or first element. We store it in temp. Then we pick the value at the second position. We store it in the memory location which was held by the first value. And then we pick what is in temporary memory location. We assign it at the second position. And we continue that way, comparing the values as we move on. So this for loop here is for comparing the values. So once we have compared all our values in the array up to the end, and we have swapped those values and kept them in order, then we move to the next loop, which is for pass. So increment pass with 1, so we move on to second pass. Then we repeat the process of comparing the element from the first one to the last, and this will continue until all the elements sorted. Then we end the comparisons and we end the passes. Then we display the content of our memory or array that is already sorted. So we initialize I1 to size do. Then we read out what is the memory location on the scores, position 0. For subscript 0, we display it on the screen. We format it to 4 characters. Then we increment I with 1. We read again what is the memory location for scores 2. Within that value, we write it out. Formatted 4 characters. So the 4 characters here, the 4 is for formatting purposes, for spacing purposes. So we continue until we have read all the elements. Then we exit the loop. And that becomes the end of that sorting technique. Let's now look at selection sort. In this method, we find the smallest element in the list and swap it with the value in the first position. We then repeat these 2 steps for the remainder of the list, that is starting at the second position and advancing each time. If there are n elements after the nth iteration, there will be only 1 element remaining. This element is already in its possession. Therefore, the algorithm requires the list to be scanned n-1 times. So simply, just as I've said for the other algorithm or the other technique, in this technique, if, for example, you have 10 elements, by the time you have scanned the 9th element, that is 10-1, the algorithm would already have been sorted, or the elements would already have been sorted. So for selection sort, sorting is carried out by first scanning the first n elements of the array for the smallest number. In other words, my dear students and the rest of the learners, this statement means that when you are doing your first pass, you compare all the elements from the first to the last, looking for the smallest element. Once you have gotten the first element, then this first element is interchanged, or this smallest element is interchanged with the first number in the array, thus placing the smallest number at the top of the list. So if you have 10 elements, and for example, you find that the smallest element is at position 7, you interchange position 7 with what is at position 1. So we swap the two elements. So we place the first element, the smallest element, at the top of the list as the first number. Then we move on to the second position, and we compare, or we scan all the remaining elements from the second position for the smallest. So the next remaining n minus 1 numbers, minus 1 is simply meaning that already one element is in its sorted position, the first element. So you no longer scan the first element. So you scan the remaining elements. That's why we are saying that next remaining n minus 1 numbers are scanned for the smallest, which will be interchanged with the second element. And the process continues until all the elements are being sorted. So after placing the first element in its position, we compare the remaining number of elements. When we get the next smallest element, or the smallest element in the remaining list, we pick that element, we place it at position 2. Then we remove the value which was at position 2, and we place it where we have removed the smallest list from the remaining list. So we continue that way until all the elements have been sorted. Effectively, the list is divided into two parts. The sublist, which is growing, composed of elements that are already sorted, which is built up from the left to right and is found at the beginning, and the second sublist of items that are remaining to be sorted, occupying the remainder of the array. This sorting technique is efficient on large lists and generally performs worse than the similar insertion sort. It's noted for its simplicity, particularly where auxiliary memory is limited. For example, if you hand the array scores, the one that I have already dealt with in the previous illustration, which contains or is composed of 4 elements, 60, 20, 10, and 40, then this array will be sorted as follows. Note, the broad elements on the left are those elements being scanned for the smallest value, while those in the right side are those that have been sorted. So in first pass, we compare all the elements, we scan the entire list. So we scan 60, 20, 10, and 40, looking for the smallest element. And we can see our smallest element is 10, and this 10 is at position 3. It is element number 3. So we interchange it with the first element. So we interchange 60 with the 10. And therefore we have 10, 20, 60, and 40. So the third element and the first elements are swapped. We then do the second pass. We compare the remaining 3 elements. So we compare 20, 60, and 40 for the smallest element. And here we can see we have 20. And this 20 is already in its possession. So we detain it in its possession. And then we do the third pass. We compare the remaining 2 elements, 60 and 40. We can see that 60 is bigger than 40. And therefore, we swap them, we interchange them. And therefore, we have our array reading as 10, 20, 40, and 60. So the fourth and third elements will be swapped. And then we have 10, 20, 40, and 60. And by that point, my dear students and the rest of the learners, the array is already sorted. So the following is a program in Pascal implementing selection sort. So the difference between this program and the previous one is simply the part or the function or the part for sorting. Otherwise, entering of the elements, we enter them just in the same way that we entered them in the previous technique. But here, I am using Pascal. So the procedure is called input elements. So we display the message, enter scores be sorted. We use for loop to read the elements as we store them in the respective memory positions in the array, starting with scores 0 all the way to scores 9. And once the value of I is equals to size, that is 10 is equals to 10, then we stop reading the elements and we end that procedure. Then we sort them. So sorting the array in ascending order using selection sort. So the procedure is select sort. We have our local variables there, and then we begin. So we do our first pass. We initialize pass to 1, 2, 10 minus 1. Remember, if you have 10 elements, we are going to perform 90 passes. That's why we have size minus 1. And therefore, we initialize our memory location called mean with the value of pass. So we assign 1 mean. And then we now initialize j with the value of pass plus 1. Already we have pass as 1. So 1 plus 1 is 2. 2, 10, do. So we compare our elements. What is in scores 0 is scores 1 with what is in scores 2. So is what is in scores 1 less than what is in scores 2? In other words, we compare them. If yes, we pick what is in J, we store it in mean. And we compare that way. Then, if what is in mean is not equal to what is in pass, if what is in mean is not equal to what is in pass, then we pick what is in scores pass. We store it in temp. Then we pick what is in scores mean. We store it in scores pass. And then we pick what is in temporary memory location called temp. We store it in the memory location called scores mean. And then we repeat again. So we move again to the next comparison. So we increment the value of pass plus 1 with 1. So we increment, or we increase, or we add 1 to the content of memory location called J. And then we find out whether it is less than or equals to 10. That is to size. If it is less than 10, continue again. So we continue doing the same. Comparing, interchanging, comparing and interchanging the positions. So we scan across the entire list, looking for the smallest value. Once we get it, store it in a memory location, as you can see. Then we pick what is where we are swapping, interchange using this section here, and we continue until we are through with comparing or scanning all the elements in the first pass. Then we increment pass with 1, and we repeat again, and that will continue until we are through with scanning and comparing all the elements, or scanning all the elements and putting them in their positions. That will end the selection sort or the sorting procedure. Then we display the elements of the sorted array using procedure sorted array. So we display that message. Then we use for loop to read the elements of the array one at a time from the first subscript to the last subscript as we write them out, formatted to 4 characters or 4 spaces each, until the value of I is equals to size. So until the value of I is equals to 10. And then we stop writing out our elements and our procedure. So we then clear the screen. So this is the main function, is the main part of the program, which contains the statement for clearing the screen, the function for clearing the screen, that is clear screen. And then we invoke the procedure for entering elements. So this is function, this is a call. It is a call to the function called input elements. We are not passing to it any parameter. Then the next one is a call statement to the procedure called select sort. And then the next is a call statement, the function called sorted array. We discussed this in my previous presentations on subprograms, and therefore, my dear students and the rest of the learners, I would like to refer you back to those presentations or parts of this series where we discussed about the subprograms, void and non-void functions, or what we call procedures and functions, and how the call statements work. Then we pause on the screen, we read blank screen, or we wait for the user to enter something, just for the purposes of being able or enabling us to see what is displayed on the screen, and we add our procedure. So the following is a function, or is a program. The following is a function. It's a function in C implementing selection sort. My dear students and the rest of the learners, remember the difference between one program and the other is simply on the part for sorting. Otherwise, the rest of the program remains the same. So here we have our function for sorting in C. It is called selection sort. There's one parameter, which is an array of type int. It has these local variables here, temp, mean, post, I, and j of type integer. Then we use for loop for our counter. And then we initialize the value of I to post. So for the first time, I is 0. So we assign 0 to memory location called post. Then we pick what is in the memory location called scores I, that is scores 0. In other words, we pick the value in memory location represented by subscript 0 in the array called scores. We assign it or store it in the memory location called B. And then we use this for loop. We increment the value of I with 1. So if it is 0, we say 0 plus 1, that is 1. So we store 1 in the memory location called J. Then we check if the content of memory location called J is less than 10. If yes, we then compare what is memory location called mean with what is in memory location called scores J. That is, for example, scores 2. We compare. We check if scores J is less than mean. And then, if that is true, we pick what is in memory location called scores J, we store it in memory location called mean. And then we pick what in memory location called J. We pick what in memory location called J. We assign it in memory location called post. And we continue that way. We continue that way. So if what is in the post, if what is in the post is not equal to I. If what is in the post, memory location called the post, is not equal to I, then we pick what memory location called the scores I, we store it in temporary memory location called the temp. Then we pick what is in the scores post, we store it in scores I. Then we pick what we have kept in memory location called temp, we store it in memory location called scores post. So that will continue, and then we then move again up. After we have done all the comparisons and we have done all the swapping where necessary, then we move up again. We increment the value of j, so that means we move on again. We move on as we compare one element after the other. Once we have compared all the elements, so we have done all the scanning, you have done the swapping where necessary, we then move on and implement I with 1. This is next pass. So in next pass, we compare our elements again, we repeat everything the same all the way. And we continue that way up to the last pass. Once the value of I is no longer less than 6, we exit. So we stop the sorting. Let's now look at insertion sort. This is a sorting technique in which the sorted list is built one at every time, with every iteration removing an element from the unsorted sublist, that is input data, inserting it into the correct position in the already sorted list until no elements remain. When the sorting process begins, the first element in the array is usually assumed to be in its possession, that is sorted sublist, and therefore the first element in the unsorted sublist becomes the second element in the array. Therefore, the first element from the unsorted sublist is copied to a temporary variable, and then it's compared with the values in the sorted sublist in order to find out its correct position. Once its correct position is found, all the elements right from the newly found position are copied and shifted one position right, replacing the element that was copied to the temporary variable, and then the element in the temporary variable is assigned or inserted in its new position. This process continues until no unsorted elements remain. Therefore, an element is inserted, a scan for the sorted, or before an element is inserted, a scan for the sorted list is done, starting at the beginning, that is left, for the correct insertion point for each of the elements from the unsorted list. The total number of iterations required to sort an array using insertion sort are n minus 1. That is, the total number of elements minus 1. For example, to sort 7 elements, you make 6 iterations. The characteristic of this sorting technique is that the algorithm is very slow when number of elements is very large. It is sensitive sorting method. Time may be saved by performing a binary search rather than a linear search to find out the location in which insert an element in the subarray. It is usually used when the number of elements is few. For example, if you have the array called scores with 4 elements, that is 60, 20, 10, and 40, this array may be sorted as follows. Note, in the left column, the bolded values are those values to be scanned, or the bold values in the right column are those that have been inserted in their correct positions in every comparison. Let's now look at insertion sort. This is a sorting technique in which the sorted list is built one at every time, With every iteration removing an element from the unsorted sublist, that is input data, inserting it into the correct position in the already sorted list until no elements remain. When the sorting process begins, the first element in the array is usually assumed to be in its possession, that is sorted sublist, and therefore the first element in the unsorted sublist becomes the second element in the array. Therefore, the first element from the unsorted sublist is copied to a temporary variable, and then it's compared with the values in the sorted sublist in order to find out its correct position. Once its correct position is found, all the elements right from the newly found position are copied and shifted one position right, replacing the element that was copied to the temporary variable, and then the element in the temporary variable is assigned or inserted in its new position. This process continues until no unsorted elements remain. Therefore, an element is inserted, a scan for the sorted, or before an element is inserted, a scan for the sorted list is done, starting at the beginning, that is left, for the correct insertion point for each of the elements from the unsorted list. The total number of iterations required to sort an array using insertion sort are n minus 1. That is, the total number of elements minus 1. For example, to sort 7 elements, you make 6 iterations. The characteristic of this sorting technique is that the algorithm is very slow when number of elements is very large. It is sensitive sorting method. Time may be saved by performing a binary search rather than a linear search to find out the location in which insert an element in the subarray. It is usually used when the number of elements is few. For example, if you have the array called scores with 4 elements, that is 60, 20, 10, and 40, this array may be sorted as follows. Note, in the left column, the broaded values are those values to be scanned, or the broad values in the right column are those that have been inserted in their correct positions in every comparison. So to sort 60, 20, 10, and 40, we begin by, first of all, assuming that 60 is already in its sorted position, and therefore we retain it at its first position. Therefore, we have our elements as 60, 20, 10, and 40. We then pick 20, that is the second element, and store it in temporary memory location. And therefore, in this first pass, where we have 60, 20, 10, and 40, we pick 20, keep it in a temporary storage location, and then we shift or we compare. We compare 20 with the 60, and we realize that 20 is smaller than 60, and therefore we swap 60. In other words, we move 60 from where it is and we place it at the position where we had 20. And therefore, we have 60 shifted to where 20 was, and the 20 inserted where 60 was. And therefore, we have our elements as 20, 60, 10, and 40. From there, third pass or second pass. In second pass, remember we have 20, 60, 10, and 40. Therefore, we pick the third element, that is 10. We place it in temporary storage location, and then we compare 10 with the 20, and we realize that 10 is smaller than 20, and it is also smaller than 60. And therefore, we shift 20 and 60 to 60, moving to where 10 was, and the 20 moves to where 20 was. In other words, we shift 20 and 60, and then we pick the 10 which is in temporary storage location, and we insert it at the first position where 20 was. And therefore, our elements becomes 10, 20, 60, and 40. From there, in that pass, remember, our elements are 10, 20, 60, and 40. Therefore, we remove or we pick our fourth element, keep it in temporary storage location, then compare 10, then compare 40 with 10, 20, and 60. And therefore, we can see that our element is supposed to be inserted where 60 is. And therefore, 60 is shifted to where 40 was, and 40 is inserted where 60 was. And therefore, we have our elements as 10, 20, 40, 60. And the array is sorted. My dear students and the rest of the learners, what is important for you to remember in this algorithm is that we always begin with the first element being assumed to be in its sorted position. Then we start now picking the second element, storing it at temporary storage location, then comparing what is in temp with what is in the first element or what is already in the sublist that is sorted. If we find that the element in the temporary storage location is smaller than the first element, we shift, we insert the element. So the protocol or the procedure is picking an element from the current position, store it in temporary storage location, compare that value with the values in the sorted list. Then we find out where we can insert our element by, first of all, shifting the elements in case we need to insert our element at the beginning or at the middle of the sorted sublist. And therefore, this algorithm entails picking an element, keeping it in temporary storage location, comparing the element in temporary storage location with the elements in the sorted sublist, finding out where it fits, shifting of the elements to create a space where the element in temp is going to be stored, and that continues until the array is sorted. So the following is a function implementing insertion sort. So we have a function called insertion sort, which is a void function. It has one parameter, which is of type integer, and it's an array called scores. We then have three local variables, one called temp, the other one called I, the other one called j. Temp is going to be used as our temporary storage location during the moving or shifting of elements or swapping of elements, while I and j are our external loop control, while j is the internal loop control or counter. So we begin by initializing I to 1. Then we check whether the value of I is less than size. Remember size we said from the beginning, it is a constant whose value is 10. So is 1 less than 10? Yes. If that is true, we pick the first, the element at scores 1. That is the second element in the array. We store it or assign it in temporary memory location called temp. And then we subtract the content of I. We subtract 1 from the content of I. So if I is 1, 1 minus 1 is 0. So we store 0 to j, or the value of I minus 1 to j. And then we check. So while the value of scores j and the value of the memory location recon j being greater than or equals to 0, then we do the following. We pick the value in the memory location called scores j. We assign it to the memory location, which is scores j plus 1. And then we subtract 1 from the content of j, and we store the results in j. So that will continue until the condition while temp is less than or equals to scores j and j is greater than or equals to 0 is not true. So once that condition is not true, then we exit on the while loop or from the while loop, and then we pick the value which we kept in the memory location called temp. We assign it in the memory location or in the array at the position j plus 1. And then we move up. We increment the value of I with 1, that is I plus plus. Then we check, is the current value of I less than size, that is less than 10. If that is true, we pick the content in the memory location, which is scores 2. We pick the value there, we keep it in temporary location called the temp. And then we repeat the entire process again. We work on the while loop until we are through with that loop. And then we pick the content of memory location content, we store it in scores j plus 1, and we end that function once all the scores or elements have been sorted. The following is a procedure implementing insertion sort in Pascal. This function or this procedure is similar to what I have already discussed. The only difference now is the syntax. So the procedure is insertion sort. We have our local variables, j and the temp of type integer. Then we initialize I with the 2. And we check if it is less than size. If it is, we do the following. We subtract 1 from the content of memory location called I, and we store the results in memory location called j. Then we work on the while. So while j is greater than or equals to 1, and scores j plus 1 is less than scores j do. So if this condition is true, we do the following. We pick the content of scores j, we store it in temporary memory location called temp. Then we pick the content of memory location called scores j plus 1. We store it in memory location called scores j. Remember, j is already what is in our for loop, what we are using as the counter, the current content of the counter. Then we pick what is in temp. We store it in the memory location called j plus 1. We pick or we subtract 1 from the memory location called j. The results, we add them in memory location called j. And that will continue. And then we increment I to with 1. If it was 2, we move on to 3. Is 3 less than size? Yes. So we repeat all this and we continue repeating the iteration until all our elements are sorted, and then we end the procedure. Let's now look at quicksort. This is a recursive algorithm that uses a divide and conquer technique. While the list of items to be sorted contain at least 2 items, quicksort divides it into 2 sublists and recursively calls itself to sort the sublists. The quicksort routine first checks to see if the list it is sorting contains fewer than 2 items. If so, it simply returns. The base case of the recursion is lists of size 0 or 1, which never need to be sorted. Otherwise, the subroutine picks an item from the list to use as a dividing point. It then places all of the items that belong before this dividing point, that is values less than the pivot value, in the left part of the list. It places all of the other items in the right part of the list, that is values greater than the pivot value. The subroutine then recursively calls itself sort to smaller sublists. There are several ways in which to pick the dividing item or pivot, but the best method is to choose one randomly. Then, no matter how the items in the list are arranged, chances are the item you select will belong near the middle of the list, and the sublists will be fairly evenly sized. Quicksort is very fast in practice as well as theory, so it is the favorite sorting algorithm for many programmers. After partition, all values before the pivot element are less or equal than the pivot, and all the values after the pivot element are greater or equal to the pivot. Even the pivot element can be swapped when reached in partitioning process. In summary, this is how this sorting technique is applied. 1, you pick an element called a pivot from the list. Then you reorder the list so that all elements with values less than the pivot come before the pivot, while all elements with values greater than the pivot come after it. That is, equal values can go either way. After this partitioning, the pivot is in its final position. This is called partition operation. Number 3, you recursively sort the sublist of lesser elements and the sublist of greater elements. It can be demonstrated as follows. If we have our same array called scores, but then we add some elements into it. So if we have the array 60, 20, 10, 40, 30, 26, and 56, we can then do the following. So we have our elements as 60, 20, 10, 40, 30, 26, and 56. Those are how many elements? 1, 2, 3, 4, 5, 6, 7. 7 elements. So we can pick an element at the middle. So we count 3 one side and 3 the other side. And therefore, we can have 40 as our pivot point. Then, from there, with our array having 60, 20, and 10 on one side of the pivot and 30, 26, and 56 on the other side of the pivot, we can then check our elements. So, like in this case, when we check the list on the right side and on the left, we can see that 60 is greater than the pivot. So it's supposed to be moved to the other side, which is as higher values than 40, while 26 is smaller than 40. So we can interchange the two. So we interchange 60 with 26. And therefore, we have our elements as 26, 20, 10, 40, 30, 60, and 56. Then we check again. We check again. We have 30. We have 30 on one side and 40 on the other side. So in other words, we can see that 30 is lesser than 40, but it is on the side which is supposed to have values higher than 40. Remember, 40 is our pivot point. So we can interchange 30 with 40. We interchange 30 with 40. And therefore, we have our array as 26, 20, 10, 30, 40, 60, and 56. From there, with our elements having been organized as 26, 20, 10, 30, 40, 60, and 56, there are now two sublists, one on the right and the other on the left of 40. Elements on the left of 40 are higher, while elements on the right of 40 are smaller than 40. So we have, from 40, we have 60 and 56. Then on the other side, we have 30, 10, 20, and 26. So we sort each of the sublists separately. So in the left, or on the other, on one side, we have 26, 20, 10, and 30. So we can pick 20 as the pivot for left sublist and 60 for right sublist. And then we sort. Remember, whenever you want to sort any of the sublists, you pick a pivot point. So we pick 20 as our pivot point. Therefore, we have 26 on one side, 10 and 30 on the other side. Well, when we pick 60 as the pivot for the other side, we have 56 on one side. And therefore, when we pick 20 as our pivot, we can see we have 10 on the side which is supposed to have higher values than 20, while 26 is greater than 20. So we interchange, or we swap 10 with 26. And then 60 and 56, 56 is supposed to be smaller than 60. So we interchange 56 with 60. And therefore, our new arrangement becomes 10, 20, 26, 30, 56, and 60. So we have our elements at 10, 20, 26, 30. And then the sublist is 56 and 60. Already, we can see that both sublists are sorted. In other words, on one side, we have 10, 20, 26, and 30. The other side, we have 56 and 60. And therefore, we just match the two. We just compare the two because they're already in order. And therefore, our array is already sorted. So our elements are 10, 20, 26, 30, 56, and 60. It is already sorted. So the following is a function for implementing this algorithm C. So my function, void function, is called quicksort. It has several parameters. One is an array parameter called scores of type integer. And then we have two other or three other elements. Two other elements or parameters. One called low of type int, another one called up of type integer. We call that function definition. And therefore, this function has four local variables, u, l, int, and temp of type integer. So we pick the value in the memory location called scores. So we pick that value, which is at the subscript, the content to memory location called low, and then to up divided by 2. So whatever value we get, that is a subscript for our current value or current element. And therefore, we pick what is in scores low plus up divided by 2. We assign that value in the memory location called mint. And then we pick what memory location called low, and we assign it in our memory location called L. Then we pick the content memory location called up, store it in memory location called low. Then we do the following. We check if the content in the memory location called mint is greater than the element scores 1 or scores L. If it is true that what is in mint is greater than scores L, we increment the value of L with 1. And then we check again. If the value of memory location coordinate is less than the content of memory location coordinate scores U, we decrement U. And then we then check again. If the content of memory location coordinate U is less than or equals to U, we do what? We pick the content of memory location coordinate scores L, we assign it to temp. And then we pick the content of memory location coordinate scores U, we store it in memory location called scores, content memory location code will be implemented with 1. Then we pick the content of memory location content, store it in the memory location code scores to implement it. And we continue that way as long as the value of memory location code L is less than or equals to U. So that is an iteration which will continue repeating for as long as the while condition is met. And then we pick the content, or we compare the content of memory location code low with the content of memory location code U. If low is less than U, then we perform quick sort. So we pass scores, the content of memory location code scores, low and U, into the function called quick sort. Then if the content of memory location called L or L is less than the content of memory location called F, we pass scores. The content of memory location called scores, L and F, we pass them to the function called quick sort. And that continues. That continues if all our elements are sorted. Let's now look at merge sort. This is a sorting technique that uses the idea of divide and conquer. This algorithm divides the array into two halves, sorts them separately, and then merges them. This procedure is recursive. It works as follows. If the list is length 0 or 1, then it is already sorted. Otherwise, divide the unsorted list into two sublists of about half the size. Then sort each of the sublists recursively by reapplying the merge sort. Then merge the two sublists back in one sorted list. Generally, you first divide the list into the smallest unit, that is one element. Then you compare each element with the adjacent list, sort and merge the two adjacent lists. Finally, all the elements are sorted and merged together. For example, to sort scores, which has 4 elements, 60, 20, 10, and 40, we proceed as follows. So we have our elements split into two sublists, equal sublists, 60 and 20, 10, 10, and 40. So you divide the array into two sublists. From there, we pick or we divide each sublist further into specific elements. So we have 60, then we have 20, 10, then 40. So we sort and merge each sublist's elements as follows. Because we have 20, 60, 10, and 40. So what we do, we first swap 20 with 10. The element in one sublist, we swap it with the element in the sublist. So we interchange 10, 20. And therefore, we have 10, 60, 20, 40. We then swap 60 with the 40. We swap 60 with the 40. 60 is the second element in the first sublist, while 40 is the second element in the second sublist. So we swap them. We swap 60 with the 40. So we have 10, 40, 20, and 60. Then we swap 40 with the 20. We swap 40 with the 20. And therefore, we have our array having elements as 10, 20, 40, 60. So, because the first sublist is already sorted, and second sublist is already sorted, with the first sublist having elements 10 and 20, but the second one is having 40 and 60, we just merge the two to form a sorted list. Generally, merge sort takes two or more sorted array and it combines them in a single sorted array. That's why it is called merging, combining. And with that, my dear students and the rest of the learners, we have come to the end of section 5. Continue section 6 of that in this topic so that you can learn more about other data structures. Congratulations for learning section 5 of that in the topic data structures. You can also access section 1 to 3 to 13 of this topic, other topics in the computer structure and programming unit, as well as other computer or ICT videos by clicking or tapping on EMELISWAP ICT YouTube channel below this video. You can also visit EMELISWAP Life Skills YouTube channel for free life skills, motivational, and inspirational resources. To subscribe to the channel, tap on subscribe button below this video in YouTube if it's not currently reading and subscribed. For any further correspondence, kindly write it to us through the email emeliswap@gmail.com. Thank you very much for listening to me. Let's meet in the next part in this series of presentations. God bless.